Okay, problem 47, and this now starts the improper integrals from section 8.8 in our book, and the rest of the problems on this review, sample exams, whatever you want to call it, is from improper integral section. So here we go. We have 0 to infinity, so infinity is what makes it improper here, of course. 1 over 1 plus 4x squared. Now, if you're writing this out, like in my face-to-face class, a little bit different than online, I guess you don't have to write it as formally, but it's, you should know how to write it out properly. But this is how you really evaluate it. You have to write it as a limit. As b goes to infinity, 0 to b of 1 over 4 plus x squared. Now, that's really a straightforward integral, and what I do on exams is from this section, I keep the integrals pretty basic in the sense of just stuff like arc functions, u-substitution, which is always important. I don't use problems from the more advanced integration techniques such as partial fractions, trig substitution. I don't use that in this section. It's already complicated enough, plus with this notation that makes it even worse. So the integral should be somewhat basic. That doesn't mean, of course, it's easy, but at least the integrals won't be difficult. So that's just arctan. You can follow the arctan formula off the formula sheet. The a would be 2, and u would be x. So it's 1/2 arctan of x over 2. The limit as b goes to infinity. And then the limit will only affect where the b is, not when you plug the number in. So wherever you plug the number in is not affected by that limit at all. So I sort of left a step out here, but I could have written it separately. You could look at my notes and see how I usually do it. Well, the next example. But put in the b, put in the 0. Well, arctan of 0 is going to be 0. So now all we have to do is figure out if the limit as b goes to infinity of 1/2 arctan of b over 2 is going to converge or not. All right, so b over 2 as b goes to infinity would just be infinity. Now we've learned in the past that arctan, that would have also come up in the L'Hopital section. The limit of arctan of infinity actually converges to a value. It converges to pi over 2. And in fact, if you forget that, you could actually take your calculator, and which I've done that in the notes also, and you could put in, like degree mode, put in a giant number, for the argument of arctan, and you would see it would give you something like 89.999. Then you could say, oh yeah, that's 90 degrees, which therefore is pi over 2. So this goes to pi over 2, and of course what makes the final answer pi over 4 is just this 1/2 in front. So essentially it's 1/2 times pi over 2, so it converges to pi over 4. All right, next one, number 48. Pretty easy integral, just u-substitution. In fact, since u equals x plus 1, I didn't show the work here. A lot of these I didn't, but you're always free to ask me. So if u equals x plus 1, du would just be dx. And so you have the general power rule at this point, u to the negative 1/2. Which you do the power rule, you're going to get 2u to the 1/2, which makes it 2x plus 1 to the 1/2. Now you put in b, you put in 0, and you put in 0. Remember, that's not affected by the limit. So basically it's 2 times 1 to the 1/2, which will just be the 2 right here. So now we have to decide what's going to happen when I put b in there. So the limit of b goes to infinity of 2 times b plus 1 to the 1/2. You put infinity in there. That's going to blow up. That's just going to be infinity. So that means the whole thing diverges, and that makes the answer diverge. The next one, 1 over x minus 1 to the 3/2 from 1 to 2. Now this is where we have the what they call, the technical term is infinite discontinuities, meaning we have a convergence. Not a convergence, but we have a discontinuity as one of the endpoints of the interval. This case, it's the 1, because the 1 would make you divide by 0. And the proper way to write that is when it's the discontinuities at the bottom, It's the right hand limit where you put the plus. When it's at the top, you'd use a negative because it would be the left hand limit. So x minus 1 to the 3/2. This time I actually worked out the u substitution real quick, but it was pretty easy. So you get u to the minus 3/2, which if you do the power rule, you do negative 3/2 plus 1 over negative 3/2 plus 1, which would give you a negative 1/2 in the denominator, which flips over and becomes negative 2. And then you have x minus 1 to the negative 1/2. So you put in 2, and you get 2 minus 1 to the negative 1/2, which that's just 1. But you see you still have the negative 2 on the outside. Now, I did an example like this in my notes. This is kind of interesting. Because if you put the 1 in there, you're doing evaluating the limit. Yeah, in fact, if you write it like this, you can see it's much more clear if you write it like that. But if you put 1 in the parentheses right here, it might be tempting, 0 to the negative 1/2, you might think is 0. Because 0 raised to any positive exponent is certainly 0. But 0 raised, and of course 0 raised to the zeros and indeterminate. That's from the L'Hopital's rule section. But 0 raised to a negative number is actually a discontinuity. Because look over here, it actually means you're dividing by 0. So that would be really easy to make a mistake and think that converges. So let's say if that exponent over here would have been positive 1/2, then that would have gone to 0. And our answer would have been negative 2 times 1, it would have been negative 2. But this definitely diverges because you're getting divided by 0. Number 50. Okay, you see the problem right here. So we write it as a limit back to infinity limit. So put the b in there for the infinity. Pretty easy integral, u substitution. But the u is just d, is no adjustment for the u here. And pretty easy power rules. You have negative 1 over x minus 1, b to 2. So you see I just left the limit right here because the limit only has to be with the b. Doesn't have to be for this other part. The other part, you just plug 2 right in there. And so the trick of whether this converges or not is will the limit part converge. And it will, because if you put infinity in there where the b minus 1 is, you get negative 1 over infinity. That's going to go to 0. And over here, you're going to have a minus 1 over 1 is negative 1. So basically, it means you have a 0 over, 0 minus a minus 1. I'll just put that here for a second. That's going to be a 0. Not a very pretty 0. 0 minus a minus 1 means 0. Then it converges to positive 1. Get that off there. Number 51. Now, you be careful because this looks like it might be integration by parts, but it is not. It is just u substitution. And that's just because of the way the exponents happen to work out here. You let u equals negative x squared. Du is negative 2x dx. So we will have to adjust and have a negative 1/2 on the outside. I'm a big proponent of changing the limits of integration, because that way you never have to go back to the original variable again. So you put b in there, it's going to be negative b squared. Be careful because the negative, only the x is being squared. So it's not, you might be thinking it's going to be positive b squared, but it's not. It's the negative of b squared. And then, of course, put in 0, you get 0. So here's our new integral. And this is good because the antiderivative of e to the u is just eu. It's pretty easy. So put eu in there. Now, I used a little trick from the property of definite integrals. You don't have to use this, but I use this a lot. I like to, just to, I think the fewer negatives you have, the less chance you have of making a mistake. So I got rid of that negative by reversing these limits of integration, because if you reverse the limits of integration, you're actually creating a negative, a multiple of negative, so that way it'll multiply by the negative you have, and therefore makes it positive. But if you don't do that, that's okay. But I like to do that. So you put in 0 here, e to the 0 is going to be 1. Now the million-dollar question is, what happens to this limit? And that's going to, since it's e to the negative b squared, that's very important because that's the same as 1 over b squared. And of course, excuse me, 1, yeah, but then it makes it 1 over e to the b squared. When you put, and then you put infinity in there, it's going to be 1 over infinity. That term goes to 0, so therefore the entire integral would converge to 1/2, because you'd have 1/2 times 1 minus 0. All right, number 52, it's going to be another one with an e. Really easy e. Just you can use basic substitution, but if you already know this, I'd mentioned that in the notes in one of the sections. That's good to go ahead and know that, just to save yourself some time. You have to be careful though that when you're talking about integrating versus differentiating. In other words, the derivative of e to the 2x would be 2e to the 2x, but the antiderivative is 1/2 e to the 2x. So there we go. As limit as b goes to negative infinity, we have 0, we have b. So if you put 0 in there, e to the 0 will be 1. Now the $1,000,000 question is what happens as it goes to negative infinity. That's very important for this one, because if you put this in here, you put the negative infinity, that gives you essentially e to the negative infinity. That's important because if this would have been positive infinity and I plugged it in there, it would have been diverged, because e to the positive infinity is diverging. It goes to infinity, in other words. But this just becomes 1 over infinity, which means it's 0, therefore it converges to 1/2. Now here's one with a basic integration by parts. I'm not likely to have an improper integral as parts on a test, but let's just take a quick look at it anyway. Good learning exercise. This could have done. You could do this by the tabular method, but I also just did it manually because it was only going to be a one-time integration by parts anyway. So if you use tabular method, that would be correct. And you'll end up with this. You'll end up with negative x e to the negative x plus the integral of e to the negative x. So now we have this. Oh, and then, okay, then I went ahead and integrated here instead of over here, which is fine, obviously. So I just kind of got rid of all the integral stuff here. So the antiderivative of e to the negative x would be negative e to the negative x. So this is the entire antiderivative right here. Now we evaluate the limit of all that. Now this couple ways you can go about this. You could treat these as two separate terms, which is fine. I chose to factor out e to the negative x, which is also fine. So e to the negative x, if you do that, it's going to leave you a, but actually there's a negative that comes out of there, and I'm using that same property. I didn't have this written in the last example, but I mentioned this. This is the property I used in the last one. So technically I would have factored out a negative e to the negative x, but to get rid of that negative is I reverse the b and the 1 and make it 1 and b. So that'll take care of that. All right. So by doing that, so like I said, there's several ways you can go about the way that once you get to this part, so this wasn't the only way to do this. So if I factor out e to the negative x and you put infinity in there, you're looking at basically e to the negative infinity is 0, and then x plus 1 would be infinity. But as we learned in chapter the section on L'Hopital's rules in this book, it's 8.7, is that infinity times 0 is actually an indeterminate form. It's not 0. We don't know what it's going to be. A lot of times it is 0, but it's not always 0. So you need to write it as a fraction, and therefore we can apply L'Hopital's rule. So I drop the e to the negative x down to the bottom, make it e to the positive x. So the limit of this, we do L'Hopital's rule right over here. In fact, I went ahead and wrote it out like this first. So if you put 1 in here, you get 1 plus 1 over e to the 1. You get 2 over e minus limit as b goes to infinity. And then the derivative would be, of the top would be 1. The bottom would be e to the x. And then when you put b in there, it would be 1 over e to the b. So this, I'm saying this result right here, when you plug the b in, turns into what this is in the green, and that's going to go to 0. So this will converge. because that term's going to be 0, and it's going to converge to exactly 2 over e. All right, so here's number 54 here has 3 separate questions, which I don't ask, multiple part questions on the same problem. Well, I guess I do sometimes ask on face-to-face classes, but not necessarily the same function, though. That's the key. It would be part A and part, like, for example, I might have a L'Hopital's rule problem, part A and part B, but they wouldn't be the same function. So 1 over the square root of x from 1 to 0 means you're going to have the discontinuity at the bottom, 0. So that's what makes it the plus limit, because it's on the bottom. And so this is pretty easy. You just do x to the negative 1/2. Learn that back in Cal 1. So put in the 1. That's going to give us a 2. 2 times the square root of 1 right here. Now we got to see what happens when you put the c in there. Put the c in there. You put 0. And now this, because this is 0 to the positive 1/2 exponent, that gives us 0. Remember, I talked earlier about 0 to the negative 1/2 would be undefined. So you end up with 2 minus 0, so this converges to 2. So now let's see with part B what happens if you put infinity, go from 1 to infinity. Let's see. Same antiderivative, of course, but let's put b in there, 2b to the 1/2. Minus 2, and then it's going to put 2. When you put 1 in there, that diverges. Part C is asking you to use that to evaluate 0 to infinity. This goes back to a property of definite integrals in Cal 1. It's not really a separate problem you can use, because that's why it's telling you to use parts A and B. That 0 to infinity can be represented as 0 to 1 plus 1 to infinity. So that's kind of the clue on this one. When they're saying use parts A and B, it wants us to add those 2 results together. But since one of those results was diverging, that pretty much took care of it, and that was the end of that. You can't 2 plus diverges doesn't mean anything. So that was a trick for that. So that concludes this section of problems.